Good afternoon, everybody. Never did I expect my slides to be so giant, so I apologize in advance for the lack of beauty in them. Now, this is kind of an advanced talk, so it's a bit of a shame it's at 4:30 in the afternoon, so bear with me. I'm a bit under the weather myself, and I probably just made the mistake of going to the quantum computing course, so my mind's a bit frazzled, but we'll see how we go. So, Kafka Streams, the DSL. The way I approached the DSL was, it's kind of the place everybody starts. I see it as the easy path to get beginning with Kafka Streams. It's very cool. It does a lot of stuff for you. It's very powerful. But after a while, it can kind of constrict you, and you can feel restricted with what you can do. It doesn't necessarily fit all use cases that you might be trying to apply stream processing to. But I'm going to show you how you can drop down into the lower levels of the Kafka Streams framework and utilize what's there and show you kind of what's possible. So quick question, who's using Kafka? Okay, who's using Kafka Streams? Okay, cool. And of those people, who's using the Transformer Process API at all? Okay, cool. So this will be a good kind of example of what you can do with it and why you might want to look into it. So just very briefly, my name is Antony. Don't let my accent fool you. I am from New Zealand. I've been working for Confluent for a couple of years now. My role is in consulting, so we travel around and deal with customers' use cases and help them design solutions around the Confluent platform and other technologies they may be using. So quick agenda, a quick reminder of what the DSL is. For those who haven't used it before, this will kind of help set the groundwork. Quick intro to the process method or the transform method. Go over a little bit about state stores, and then we'll go over a couple of customer use cases from the field. One focusing on time and aggregations, and the other focusing on performance and concurrency, and a little bit about optimization at the end. So when we talk about stream processing, we generally talk about topologies. This is an example of a topology. Generally, message flows from sort of the top to the bottom, we say. You have message processors connected to each other. The DSL is all built on top of processing nodes, even though you don't necessarily see them as such in the API. So this is what an example of the DSL looks like. There's not going to be much code. This is one of the two, I think, examples in the presentation, so don't be concerned. So at the top, you can see we're constructing a Kafka Stream instance from a topic. We're running what we call a stateless computation on it. That means that the processing in this node doesn't acquire state. We're simply doubling all the input integers coming down the stream and outputting that to another Kafka stream called doubled. Below that, you can see an example of stateful computation. So this is where the framework is gathering together and managing state for you in order to do the processing. You can see we're filtering out, getting all the odd numbers, and then simply summing them all together at the end. So in the DSL, this is kind of an example of some of the methods you have. We talk about this thing called stream and table duality, where a table is a sort of a snapshot state and time of a stream of messages. You can convert between the two sort of models or views, depending on what type of functions you apply to either the stream or the table. And as you saw before, we have maps, filters, joins, branches, reducers. And then to go back from a table to stream, you apply the toStream function. And it's pretty straightforward. And there's a whole bunch of stuff the DSL can do for you, but as I said before, sometimes you need to drop down. So what does the process method or the sort of the PAPI do for you? Well, it gives you flexibility. And the primary flexibility you get is what we call write access to the state that's being gathered and managed for you. Otherwise, you normally only have read access. So this gives you a whole bunch of freedom, and it's freedom really to have write access to these state stores. You can do a whole bunch of stuff. You can do a lot of stuff with the DSL as well. You're not really restricted to just the DSL functions. You can do a whole bunch of stuff inside them as well. But it's really focusing on how you can leverage the write access to these state stores. I'm going to talk about that next. So it gives you power. It's kind of, you can kind of think of it as a DIY. So once you drop below the DSL layer, you have to do a lot of stuff yourself, and you have a lot of power. But with great power comes great responsibility, but not too much. This is the example of the process function on the DSL API. It's not what we actually call the processor API, because when you drop really down to there, you have to deal with a lot more nuts and bolts that you don't really need to in order to get the full power of the core of the processor API, which is really that write access to the state stores. This is actually what the interface looks like. It's slightly simplified. I've cut out a couple of the boilerplate things, but it's really straightforward. Give me a message, and then you do something with it. This is sort of analogous to the map function in the DSL, but you'll see shortly how it differs a lot. And the sibling of the process method is the transform method. They're pretty much the same, except for those of you observant in the audience, you may have noticed this returns a value. The other one returns voids, has no return value. That's simply it. So we distinguish between those two types of methods by saying one is terminal and one is non-terminal. So terminal meaning that the stream stops at that point. You can't continue down a topology. Whereas transformer is non-terminal. You can chain on more functions. So this is an actual example. We're not going to step through it. It's pretty cool that you can actually read the code when the slide is this big. It wasn't designed to be like that. But this is a real example of something I'll touch on toward the end, what we call synchronous state checking. There's the init method that I didn't show you before. You just set some things up there. You can see the process function and then some boilerplate down the bottom. So the question then is, when do you use one versus the other, right? So the PAPI versus the DSL, or you can think of just the process and transform versus the DSL. And the question is, being a consultant, my favorite answer, it depends. The DSL is easy. You can do a lot with it. And you can do even more with it once you get comfortable with the functions and get clever with your data structures. If it fits nicely, use the DSL. It's definitely the easier way to go. Now, with the processor API, though, you can create a whole bunch of reusable functions. You can do the same thing with the DSL as well. With the processor API, you get that write access to the state stores. You can shoot yourself in the foot, so be careful. And I'll show you a couple of gotchas toward the end. But what I see a lot of the time clients trying to do is bend over backwards, trying to fit what they're trying to do into the DSL model of working. And the sort of result is complicated. It's hard to see that it's correct, and it may not even work for reasons they don't foresee. Whereas if they actually attempted implementing it at the process or transform level, you can realize that it's actually much easier than it may appear, and the solution appears much more correct, which is always good. Now, the real answer is that use both. In fact, use the DSL and then dynamically drop down into that transform level when you need to. So this is just a snipped example. So taking a stream, grouping it by a key, applying the reduce function, which gives you a sort of a K table, mutating it back into a stream again, applying a transformer to it, maybe doing some stateful processing there, using the DSL again to apply the map function, and then outputting to another topic. So the answer is use both. So I keep talking about state stores. What is a state store? Well, all stream processing frameworks, to do things more complicated than simply multiplying values together or something, generally have to gather state. Now, the state has to be put somewhere. In Kafka Streams, by default, we put it into a local key value store database called RocksDB. It's very high speed. It spills over to disk, so you can put a lot of data into it. People get concerned about it fitting in memory and things, but you don't really need to worry about that too much. And by the nature of Kafka, we actually manage that RocksDB database for all the state stores that need to be created or that you create yourself. And we back it into what we call changelogs in Kafka and things. I don't need to go into details of that. But by doing this, by backing up that state store, those RocksDB values, into a topic inside Kafka, the RocksDB database then also becomes distributed, redundant, highly available, and then there's backups inside Kafka. So the state that's gathered in your Kafka Streams instances, you don't need to worry about losing that. You can wipe out a Kafka Streams node or your entire cluster, start it up again, and it will just restore itself from that backup inside Kafka. You can also think of the state stores as sort of an optimization, because the state could be stored into like a Redis instance or a Postgres database sitting outside. But by having the state on the instance where the stream processing is happening, there's no, well, in some cases, there's no serialization payment. There's definitely no network hop. So you can kind of think of it as an optimization. And there's this other thing called interactive queries. Now, interactive queries is the ability for you programmatically to dip down into the state that's being generated by the framework and pull out those values. So, for example, if you're running aggregations like counts and things, in the DSL, you can get a read-only access to that state and pull out those counts and aggregations dynamically from other threads. So, for example, you can embed Kafka Streams into an HTTP server and then respond to an HTTP request, give me the current count for this current thing, and you can, from one thread, dig into that state store and pull out that value. And then you can also basically route these query requests across your Kafka Streams instances. So if you have 100 KS nodes running your stream processing application, it doesn't matter which node you query. As a client, you don't need to know where the data is. The framework knows how to route your request for you. So what can you do with state stores and process and transforms? This is sort of an example, sort of a taste. Deduplication, we have a really interesting deduplication example in the Kafka Streams examples repository in GitHub. You can do things like secondary indexes. So typically in the state stores, it's a key value state store. So there's no secondary indexes. So if you want to be able to store like accounts against accounts ID, but then be able to query against an email address instead of the account ID, you can maintain a secondary index. If you need to do something periodically against your data, we'll talk about that later. You can do something called punctuations. You can also implement TTL caches inside state stores. So if anyone's used K-tables before, you know there's no time to live for the K-table entries. We'll talk about that a bit later. And you can also implement synchronous state checking. So by the nature of Kafka Streams topology compilation, topologies actually get compiled into subtopologies that can run in parallel. So if you need to synchronously check some state before you respond or emit a response event, you can do that with this. You can't do it with a normal K-table, as you might think. More advanced uses, so state recalculation, that's one of the examples we're going to go into. Expiring data efficiently, so that's one of the TTL examples. You can use it to work around shortcomings in the DSL API. So for example, one of the things that the DSL currently doesn't do is global K-table triggered join. So if you're joining a stream against a global K-table, only new messages arriving on the stream will trigger a join lookup to emit a join result. If a new entry arrives in the K-table, nothing happens. But you can basically implement that yourself a lot easier than you might think in using the processor API. Okay, you can also do compound keys, and this is actually an implementation detail of how Kafka Streams does windowing. So you can, again, remember I said the state store is a key value database, so you can actually get clever with how you create your keys such that you can do range scans against combinations of key values. So for example, truck ID and time window. It's pretty cool. And you can also do things like one-to-many joins. So for example, if you have one-to sort of many entries, maybe you have like an order with order items, and the order items might grow up to 10,000 entries, slightly unrealistic example. You don't want to be reading and updating a single entry where that value could grow from one entry to 10,000, because that read, update, write loop is going to get worse and worse and worse in terms of performance and data size and things. But by compounding the key with the order and order item ID, instead of doing read, update, update, insert, you're now just doing insert, 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 insert on the state store. So much, much higher performance, and avoids building much larger compounded key values. You can also play with time, like I mentioned before, so compound the key with a timestamp, and then you can query against your model object and some time. The secondary index, as I mentioned before, so with the compound keys, you're restricted to generally one compounded key. So for example, truck ID or account ID and email. You couldn't do like account ID and account type in a single compounded key. But using state stores, you're not restricted to any number of state stores. You can create as many secondary indexes on your model object as you like. So before we go into one of the examples, I just want to remind you how time works in Kafka Streams. And this is, I've blatantly stolen this slide from one of my colleagues, but it's a really good example. So there's three aspects to time that we look at in Kafka Streams. One that we call event time, one we call processing time, and one we call ingest time. Event time is when the thing really happened, when basically you can think of when the producer creates an event and then sends it off. Ingest time is when Kafka receives the event. And then processing time is when Kafka Streams reads the event from Kafka and starts doing something with it. So for in this example, you know the Star Wars movies, we watched them as they came out, but in the Star Wars universe, they happened in a very different order. That's quite an important concept. So you can see here event time in your producer app, ingestion time in the brokers, and processing time in the Kafka Streams cluster. So, the first case study. This is about this is quite niche, quite unique, but it demonstrates the principle quite well. So in this instance, let's say the customer has many devices out in the field. Let's call those devices trucks, just for sake of argument. And every now and then, this truck sends off a message through some big long pathway to get to Kafka about the state of itself. So for example, are its windscreen wipers on? What's its current acceleration, G-forces, all sorts of stuff. However, there's one little detail that us as the back-end engineers or stream processing engineers can't control, is that the third party who created the device that reports this information on the trucks only reports variables in the trucks that have changed in each message it publishes. So for example, if the windscreen wipers are on and they stay on for 3 hours, every 5 minutes when it reports its message, its state, it doesn't include the windscreen wipers because the windscreen wiper state has not changed. So at time 1, we receive a message saying they're on, and then at time 2, we receive another received another message of state from that truck, but the wiper's state is missing because it hasn't changed. So we can only assume the wipers are still on. Okay. So what's the problem, you may ask? Well, in this situation, we receive messages out of order. Again, we can't control this. At the time 1.5 between the two buckets, this is missing, and we may receive it sometime in the future. And when we do, we may need to go back and recalculate all the buckets from this side on where we have incorrectly assumed some state of the truck. So at time 3, we now receive this bucket which was missing before, which now fits actually between these two. So we incorrectly assumed the windscreen wipers were on, and they're actually off. So we need to go back and recalculate all those future bucket states. And this could be hundreds, it could be 1 or 2, but it could be lots of different state aspects as well. So I call this dynamic recalculation of dependent data aggregates on demand from out-of-order arrival of data. So it's a bit of a mouthful, but that's really what it is. So we need to go back and recalculate. So if we're using the DSL, and the DSL has lots of functions for doing aggregations, accounts, windowing, and bucketing and things, it's definitely the way to start. The DSL cannot trigger an aggregation calculation to run for a given time window that you define unless a message arrives in that time window. So we can't update aggregations that haven't been triggered from a message arriving in that time aggregation. Now, there is a potentially messy solution that I did work with the client on. Well, we discussed it. And it's called synthetic events. And it's when you produce an event back into your input stream that wasn't really a natural event from your data source. So in this example, we receive the missing bucket, and then we try and calculate messages that would fall into all those future buckets of time, and then pump those into the input topic artificially re-triggering those aggregate calculations to rerun with our new state. The problem with this is that it's difficult to do. It's difficult to calculate all those time windows. You would have to track how many you would have to calculate, or calculate based on time how many you'd have to create. It pollutes the input stream with fake data, with artificial events that aren't really real. It's unnatural, it kind of smells, and because you're producing events back into the input topic, you actually have to break out of the Kafka Streams transaction context, which if you're using exactly once, kind of breaks your transaction semantics. So into the process method. What we can actually do is, and this is quite simple, is that we track our own aggregates. We do our own counter aggregation functions. And using that concept we talked about before about compounding like device IDs with time keys, it's actually quite easy to do. And we can then run a range scan on the state store for a given truck and query any potential windows in the future that we've been tracking ourselves, rerun our business logic on those aggregates, and output new results. And this is all obviously keeping within the transactional context, so there's no break. So this is really a natural solution. So we receive 3. We know the windscreen wipers are actually off. So like I said, we query our state store for all future window aggregates that we may have already calculated, regardless of how many there are. We don't have to know how many there are. And we simply rerun our business logic and update that state in that state store and potentially emit new state update messages down the topology to update our downstream consumers that, whoops, we were wrong, something's been updated. Out of our control, because we received the message out of order. Okay. So, punctuation. Like it says, you can kind of basically think of punctuations as cron jobs for your state. You don't necessarily have to do operations on your state, but it's a timer function that you set up inside a process or transform implementation that you can run regularly against your state to perform some operation. Now, the first time I encountered this, I used it as a solution to solve. I did a multiplayer game streaming matchup framework where I was creating multiplayer groups of 10, but after some time, if 10 players hadn't arrived, I wanted to close that group and allow those players to begin playing the game. And you can do that like every 10 seconds, run your punctuator. You can do all sorts of things with it, and I'll show you a real example later on. With punctuation, there's 2 really important concepts of time. One is called wall time, one is called stream time. And so stream time actually came first, and it was really confusing. And then wall time came, I think, in 10.2. So it's been around for a while, but not when I first joined. And basically, wall time is what most people want. It's what you usually think about when you think about cron jobs. When you say you want to execute something in 10 seconds, it's usually 10 seconds in real time, Earth time, clock on the wall time. Now, stream time is really interesting. If you tell a punctuator to run every 10 seconds but on stream time, what that'll do is it'll use the time extractor that you set up, and it'll run based on the time of the messages being ingested, however you configure your time extraction. So for example, if you set it to run every minute, and you started your Kafka Streams application from the beginning of the input topics again, so you reset your Kafka Streams app and run it from the beginning, say it takes your app 10 minutes to run through 6 months of data, that stream time punctuator is going to run thousands and thousands of times, even though it's only been a few minutes and you told it to run every 10 seconds. Whereas the wall time punctuator will only run every time it's real time 10 seconds. So very, very big difference. Okay, so one other example I tapped on before was the time to live for K-table entries. So one of the common misconceptions of a K-table is that if you create a K-table from a topic that has a retention period, some people expect that the K-table will mirror the retention time of the topic it's created from. So for example, let's say you create a K-table from a topic that has a retention time of 1 day, you may expect the K-table entries constructed from that topic to remove its entries after 1 day, but that doesn't happen. K-table has no notion of some TTL or retention time for its entries. So generally, we advise people to not create K-tables from unbounded key sets of input topics. So that's input topics where your key set grows infinitely. So for example, your key is a random number, or it's a transaction ID, or some log ID that's always going to be unique, so always growing. And what that impact has is that your K table will always grow, and because there's no TTL on K tables, your Kafka Streams processing nodes may run out of space. They'll spill out to disk, but the disks will eventually fill up at some point. Whereas if it's a bounded key set, for example, something like user account, or account ID, or truck ID, you generally have 1,000 of those or 10 million of those. It's not something that's going to grow infinitely, so you can very sort of clearly estimate how much disk space you'll need to record those things. However, if you do want a K table or a key value lookup type model against a point-in-time version of your keys on an input topic that is unbounded or does have a very tight retention time, you can mimic this behavior and give yourself a key value store that does have a TTL by using the punctuator semantics and a compound key of the model ID and time, which allows you to basically scan through your state store, look for anything that's beyond your retention time, and then just remove those entries from the state store periodically, maybe once an hour or once a day or something. Now, of course, this wouldn't have all the lovely things that a normal K table has in the DSL, so you would have to create your own joins and all that kind of stuff. But if you just simply want to go do interactive query lookups against the state in the state store, then this is a very simple solution for doing so. Okay, next example. So this one was really cool. This was for a TV game show around cricket games, where users were asked to, for any given, I always get my terminology wrong, and I'm Kiwi, so it's very embarrassing. For any given bowl, how many runs the batsman is going to get for this bowl. And just to make it a little bit more complicated, there's millions and millions of viewers who are going to be answering these questions. The non-functional requirements are for some very, very low latency, so if people get the question right, they want to know within a couple of seconds at most. The games are all live. There's multiple games going on at the same time. Questions can overlap each other, so that one question doesn't necessarily finish before another question starts. Viewers can respond to the questions early. They can respond late. And we don't know when the answer is going to arrive because we have to wait for the actual game to progress and for someone to input the given number of wickets into our sort of game feed. So the first approach that was taken for this before we got involved was a topic per possible answer for every question. So let's say you had 5 options for a question. The customer would create 5 topics and an answer topic. And then the consumer would listen on the answer topic when it would arrive, see what the answer was, and then just start consuming from that corresponding topic and ignore the other topics, potentially, because maybe in this case they didn't care about people who got the question wrong. And then just feed from that topic that got it right, and then process the correct answers and do whatever. And it worked. The problem is that we all know that creating a topic per thing in Kafka is a Kafka anti-pattern, because Kafka has a restriction on the number of partitions a given cluster can support. And very quickly, this became unwieldy for the application developers, because they had to manage creating and deleting thousands of topics every day to support multiple games, multiple questions. And it made the cluster unstable, and the result didn't perform all that well. Now, how can we solve this? Well, you could do a stream-to-stream join in the DSL, using the window retention period to keep early arriving responses so that you can later join up when the answer does arrive. And the problem with this is that it's inherently single-threaded, because in order to join the correct answer when it arrives, you have to use the same key as all of the responses. So this means that for a given question running at a given time, everything has to go to a single partition, which means everything has to go to a single Kafka Streams thread. So you can't make this highly concurrent if you use that approach. Another option you might think of is not using the question ID as the key, but using the response ID. So distributing the responses across a highly partitioned topic across your entire cluster, and then joining against a global k-table. Because as we all know, the global k-table will have a copy of the answer on every Kafka Streams instance. Now, the problem with this is it works once the answer has arrived. So the answer will be in the global k-table, and then new responses will join against it as they arrive. But all the early answers that got there before the answer was available will be dropped effectively. If you did an outer join, you would get null results out of the join for the early responses. So it's kind of half a solution. And we want to make it as attributed as possible to get the latency as low as possible. So what can we do? So this is a visualization of the problem. So millions and millions of users, answer arrives. These are the responses in the outer circle. Then once the answer arrives, we join against it. And then as new answers are arriving beyond that, we join straight away because we already have the answer. So as I said, the DSL stream-to-stream join is inherently single-threaded. The columns represent partitions. When the answer arrives in the other stream, we can then join against it. It's a very, very easy implementation to do. Stream-to-stream join is very straightforward. But as I said, it's inherently single-threaded. So for example, if you had 4 million responses, you don't really want to have to be restricted to processing 4 million responses on a single thread when you have this big cluster farm. And as I said, with the global k-table, it only solves half the problem. So, as you might have thought, here comes the process or transform method with the state store. With the early responses, it's really quite a simple solution. With the early responses, we store them into a state store. So we hold onto them into a custom state store, write them to that RocksDB database that gets backed up into Kafka. Using a response ID is the key, so it's fully distributed across the entire topic. And we store the join misses. And then periodically, in a punctuator, we query the state in the global k-table, because even though global k-table is a DSL level object, we can get read access to the state store that backs it. So we can poll that global k-table, poll that state store every, let's say, 100 milliseconds because it's in memory to check if that answer, that result has arrived for the answer. And if it hasn't, that's fine. And then when it arrives, of course, that poll is going to hit, and then we're going to join against all of the responses we received so far, process them out, distribute it across all of our threads running in the Kafka Streams cluster, send out those results. And then when the late responses come, late defined as simply arriving after the answer was available, they will just simply be joined as per normal against a stream to global k-table join. Fully distributed and no single-threaded bottlenecks. So another sort of cool thing you can do is future event triggers. I worked on this with one of our customers. And this is sort of cron jobs, but way off in the future, potentially. So let's say you have a customer who registers they're going to change their address at some point in the future, or they have credit cards that are going to expire. And you want to produce an event when that happens or take some action. And that's very simple to do. You have two choices: either schedule the punctuator to run at that date and then manage the state of all your scheduled punctuators because you have to restore if you die. Or you can just save in your state store a list of future things that should happen, and then in your punctuator every, let's say, 1 minute, check that state store to see if there's anything that you should do yet. And that's probably actually the simplest solution. Also, time is a secondary index. So we've spoken about this a little bit. So you can do range select on all keys. So the state store gives you get, put, and a range select operators. And you can delete your entries when you need to, and you can poll the state perhaps even every second because it's all in memory. And then when your punctuator runs successfully, then you can remove the punctuator, unregister it, and then schedule the next punctuator to run as you need. This was also an interesting one. So if you have what we call CDC, so change data capture, so you can just think of it as simply capturing the changes to data in some data source. So for example, maybe you have a Postgres database and you're updating a user profile and changing an email address. CDC is just capturing those changes to that email address as persisted messages in Kafka. And that may be coming from a database or some other source, it doesn't really matter. And in this case, the problem was that the CDC source was only producing full snapshots of a document. The problem was we wanted to know what had changed. And so some databases will give you a delta, so they'll give you delta messages, so exactly what has changed. Other systems will only send you full state. So the problem was then is, can Kafka Streams help you with generating the delta messages from those messages of full state? And yes, the answer is, of course, it can. You can either derive deltas from full state stored in a state store, which, yes, that means you effectively have to have a copy of your source database inside Kafka Streams and Kafka in order to do a delta comparison against. And that's quite simple. But you can do it with k-tables as well. And you can do it in a very performant and a little bit harder to read way, just using a tuple value as the value in a k-table instead of just the single state value. Because just as normal Kafka messages with Kafka Streams, you can store any type of binary format inside the key or the value. So you're not restricted to perhaps only keeping a copy of the document as the value. You can keep a copy of the document and the last generated delta, so that when you receive a new state message, you can compare the new state with the old state and then record that delta inside as a tuple of values inside the k-table entry. The stream processor one is, I think, probably a little easier to understand, but once you get past the idea of tuples as a k-table value, the DSL method is actually quite straightforward as well. However, if for some reason you wanted to do TTL on those delta entries, let's say you have a giant database and for some reason you only care about the deltas in the past week, let's say beyond a week you know the document will never change or you don't care about the change. If you use the DSL method, you're then stuck with these entries inside your k-table forever, taking up space that you don't need. If you use the process and state store technique instead, you can then run punctuators and remove those entries every day or week as you desire. So the code example I showed you at the beginning was actually a very straightforward example of doing exactly this, synchronous state checking inside a Kafka Streams topology. And we have examples of using this to do things like checking account balance before you allow someone to withdraw. And the example earlier in the slides is actually checking if an email address is available before you allow that email address to be officially held by a new user. And again, as I said earlier on, because of the nature in which a topology is compiled into subtopologies and things can run in parallel and an eventual materialization of k-tables versus input stream processing, you're not actually guaranteed that a k-table you might be comparing against is up to date. It may have fallen behind its input topic that it's hydrating from. And if you go to check, say, if this email address is available yet, that message that tells the k-table, no, it's not anymore, may not have arrived yet. So you can't rely on this to do exact state checking if you want to lock something on that condition. But you can do it with the state store, because you can basically make writing this entry to a state store effectively in a transaction in the same as transaction that you output the event saying that email address has now been taken. And we have a really nice example in the Kafka Streams repository of doing the account balance version of the example. It's a really full, nice example. Routing is an interesting problem for that. So if you have a new user request coming in through your web gateway, and let's say you're relying on Kafka Streams to do your checking to say whether this email address is available or not, you have to make sure that either you route the request to the correct instance that holds that knowledge about that email address, or you send the message anywhere and then rekey on the email address such that Kafka Streams sends it to the correct node eventually that does know that state. But that's sort of something you have to think about. Optimizing topologies. So some things that you want to do, you might need to combine multiple DSL operations to achieve. Now, you might know, because inherently to your use case, that you might be able to combine these things into one operation and maybe avoid what we call some rekeying operations that have to send messages back to Kafka and read them back again, you can potentially combine these into a more sophisticated process or transform function and avoid some of that overhead. But beware of changing your key when you write entries into your state store. So when you restrict yourself to using the DSL and K tables, Kafka Streams takes care of all this rekeying logic for you. So if you use the function map versus map values, it doesn't know if you've changed the key. That's why the map values version of that function exists in the DSL, because if you use map values, it knows you haven't changed the key, so it doesn't need to do it knows it doesn't need to do a rekey operation. So I worked with someone where they were having this problem where they were complaining that their interactive queries weren't returning the correct results or weren't able to find the data, so they implemented this whole layer where they were tracking the data themselves. And upon further investigation, we realized that they were consuming messages inside their processor that had, let's say, an account ID as the key, but when they wrote the value to the state store, they weren't using the account ID as the key anymore. They were doing a quick switcheroo and using the email address as the key. And because that means you're effectively managing your key and data locality yourself without telling Kafka Streams or without letting Kafka Streams do it for you, Kafka Streams' interactive query capabilities is no longer able to track where the data is because you've shifted it under the hood without telling Kafka Streams. And so if you wanted to do something like that, what you would generally do is before saving that new entry to the state store with the email address, you would first route it back through a topic keyed by the email address. That way, the email address's location in terms of the Kafka Stream instance that looks after it would be consistent with the partition that that key would have been published to, which is the system Kafka Streams uses for locating your data for you. So moral of the story is when you're doing interactive queries and state stores and changing keys, just be aware that these sorts of things can happen. So this is one of my favorite new features coming in 2.1, global topology optimization. So we're changing the topology compiler from a one-phase solution into sort of a two-phase solution, so that instead of the engine building the topology as it reads through your DSL functions, it will do a first pass and then do a second pass, and in that second pass try to apply optimizations to your topology as a whole. One example of these is, again, these rekey operations, which can be a source of much increased latency in your whole flow as a whole, where if you're doing, for example, again, map functions down into different branches in your topology, Kafka Streams originally didn't know that you were doing these things, and so it might have to do that rekey 3 times in 3 different parts of the tree. It works, it's just slower because it has to do it 3 times. Instead, what this global topology optimization will do now is recognize those patterns and push that rekey operation up the tree so that all 3 branches can share that same rekey operation. So you go from 3 to 1, or n to 1, depending on what you're doing. So that's a pretty big one. That's the first global optimization coming in 2.1, and there'll be more following after that. Yeah, and if you know what you're doing, it's a bit more advanced. If you recognize, and you're running previous to 2.1, if you recognize that this is happening, you can actually force Kafka Streams to do the rekey operation up the topology by using the through operation, which forces the messages to go back through into a topic and re-download it by KS, which is forcing the rekey operation effectively. And speaking of versions, by the way, this is not on this slide, there's something not many people know. You don't actually need to run the same version of Kafka Streams as you're running brokers. So it's kind of nice because all of the smarts with Kafka Streams is client-side. Let's say. But you can quite safely run a 2.1 version of Kafka Streams against a 1.0 cluster. So that's really nice. You get you can upgrade your Kafka Streams applications without having to wait for your operations team to upgrade your cluster. So another comparison that we make quite often is KSQL versus the processor API, or KSQL versus Kafka Streams. KSQL is the relatively new. It's been out for quite a while now. SQL engine on top of Kafka Streams. And it's a really cool engine. It's a really cool product. And you can kind of think of it as another abstraction from Kafka Streams. So you can think of the raw consumer-producer API, then you have your processor API that abstracts that. Then you have your DSL API that abstracts the processor API. And then you have KSQL that abstracts the DSL. So KSQL is a really easy way to get into Kafka Streams. It kind of looks like SQL. It's not exactly SQL. But you can do things like counts, aggregations, joins, a lot of the most common DSL functions, just as something that looks like a SQL query that you submit to a KSQL cluster and sort of runs forever and never finishes because it's a stream processing engine. It's also a great way to get at Kafka Streams functionality from outside a Java environment. So Kafka Streams is only implemented in Java at the moment. You can use it from other JVM languages. Like there's a really nice new Scala API that's recently come out that's cool. And any other sort of generally intercompatible JVM language. However, if you're running in C or Rust or Go or something, there is no Kafka Streams framework for you. But you can leverage KSQL to get at that functionality from your, let's say, foreign language. And recently introduced as fully documented and supported user-defined functions in KSQL. So we have some people from the company going around giving talks about sort of implementing machine learning functions as a UDF inside SQL. So you're no longer restricted to the defined functions that come with KSQL, like count aggregate. You can plug in any function you wish. So you can do some really cool stuff there. And in the new version, we also added aggregation functions, which are a bit more complicated, but open it up. So that's the end of the talk. Thanks for coming. Thanks for listening. Moral of the story is, by all means, start with the DSL, start with KSQL. Just be aware that the process and transform functionality is a lot easier to use than you may think. And you get a lot of flexibility and power from getting write access to those state stores. The Kafka Streams examples repository is a great place to have a browse around. Ben's videos on YouTube, he's sitting right here, is another great place. Go check out his talk tomorrow morning, it's really good. Yeah, we're hiring and we're serving as well. Get in touch if you want to speak to us. Thanks very much.